Hello. Okay, so in this video, I want to talk about air resistance and one of the ways we might model it based on some physical reasoning. And then on the basis of that model, try to solve a differential equation where we have air resistance in our net force equations and use a technique called separation of variables to do that, which I'll explain when we get there. But first, I want to talk about air resistance itself and see if we can reason out a model for how it might work. So imagine I've got a box here. So just some object. For simplicity, I've made it a cube. And I've got a bunch of little air particles here. They're blue. I've drawn a kind of a dashed cube here. And what this represents is where the block's going to move. So if the block has some velocity, so let me give it some velocity v this way. Then over time, the block will move from where it is to this spot over here. And as it moves, it's going to displace the air. So as it moves this way, that block is going to push all those air molecules out of the way. Another way to say that is that the block will exert a force on all of those air molecules. And therefore, the air molecules will exert a force back on the block this way. And that's the force of air resistance. That's what we're trying to quantify in this model. So let's think through how that might work. So I'm going to define some stuff that's going to be useful here. One thing I'll define is this length here. Let's call this delta x, right? And then it takes some amount of time to go forward that amount based on the velocity. And we can also say for sure that if this block is moving at constant velocity, just to simplify our model for this moment, or at least the velocity is constant over the time period we're considering, then the velocity is going to be that delta x over that delta t. So we have that relationship. Also, something that we might want to define would be the cross-sectional area of the box. And so I'll define that as the area of this face as A. So that's the area of this face that's kind of pushing the actual air molecules. Okay, so let's try to understand what's going on here. So let's consider the force that's acting on these air molecules. So if I wanted to understand how that worked, I would say that the force on the air molecules is equal to their mass times their acceleration. The force is what we're trying to quantify. So we're going to start looking at how they accelerate to get a sense of what the force is doing. So, okay, so if we, and these are for the air molecule. So this is net force on the air. If we figure that out, then we should know the force of air resistance that this block experiences, because the force on the air will be the same in magnitude to the force that the block experiences here. So let's think this through. So the acceleration can be written just as a change in velocity over a change in time. The mass of the air molecules, there's a bunch of air molecules. And if we imagine them as some sort of continuous thing with some continuous density rather than discrete particles as I've drawn them here, then I can write the mass in the following way. I can say it's the density of the air times the volume of the air that's actually feeling this force. All right, so but what's the volume of the air? Well, it should be, if we're considering this time period here for the change in velocity, then it should be all the air that gets moved out of the way in this cube right here, right there. So that's the volume of the air that we're considering, because that's the volume of the air that actually gets pushed out of the way as the block moves from this spot to this spot. Okay, so how much volume is that? Well, it's the cross-sectional area of the box times the length of the motion, how far the box moves in that time. So I can write the volume of air that's moved as the cross-sectional area times delta x. Okay, so again, what this represents is the mass of the air that's actually moved out of the way. And this represents the acceleration of each of those air molecules as they're pushed, or the acceleration of the air as a whole. So we're going to make an approximation now, and I want to reason through it. So the approximation I'm going to make is that the change in velocity for the air molecules is just the velocity of the box. So why does that make sense? Well, if we imagine that maybe the air is still to start. So let's say on average, the air in this cube is still to start. Then we can approximate what the box does to it as the box moves is the box imparts a velocity on all those air molecules. So it causes the air molecules to move. And it's a reasonable approximation or a reasonable assumption to make just to get a sense of what's going on, to say that the box accelerates the air molecules until all those air molecules are going the same speed as the box. So in this model, it takes all these air molecules and just pushes them in a column that way. And so the effect the box has is to push the to speed those air molecules up until they're going the same speed as the box. So in this model, if the molecules start at 0 velocity and end up going velocity v, then the change in velocity is just v over delta t. And this is looking like something. Now what I'm going to do is I'm going to do kind of a trick, and I'm going to shift this delta t over here so we can see that I've got the density, the cross-sectional area, and then delta x over delta t times v. But we already know that delta x over delta t is just the velocity again. So I sort of secretly have two factors of velocity here, or at least I can write it this way. Okay, so here's a model for the force on the air molecules. So this is a model, simplified model, for the force of air resistance. And again, we can say that because we found the force exerted on all this air, which should be equal in magnitude, opposite in direction, to the force exerted on the cube by the air molecules. So that's some force that goes this way. And I'll write it like this: force sub AR for air resistance. Okay. This is interesting in many ways. So we know that this is an oversimplification. We know it's not a perfect model. We know that the air isn't just going to cleanly accelerate in a column from 0 up to the velocity of the cube. We know that's true. But this gives us a sense of the dependence of the force on velocity, given the set of assumptions that we made. And the important part here is that we have some force that's proportional to velocity squared. That's a model that we could check. And in fact, we are going to check the validity of that model in a lab that comes later. But for now, we can try to take this model and predict what the motion of our cube might be, or a box or something like that, if this is the model for air resistance. And so I want to do that now. So let's set up a problem. So let's say I've got a box and it's sliding on the ground. It's got some mass. It starts with some initial velocity, v naught, this way, and frictionless ground. And the question is, how does the motion of this change over time? Let me make this a flatter ground. That's a little bit better. All right. So how does the motion of this change over time? How does the speed change over time? Let's start there. Or velocity, I should say. How does velocity change over time? Okay, well, we can approach that with Newton's second law. That's normally the way that we approach problems of this type. So I'm going to draw my free body diagram. It's just the force of air resistance. there's no other forces pushing this box. You started off with some initial velocity, you let it go, and then you just let air resistance act on it. There's no friction, so we're not considering that. And you see what happens to the box over time. So Newton's second law would say that the net force on the box is equal to MA. So MA is equal to the net force on the box, which is minus force AR. I'm going to write, and we're using this model that we just kind of derived. I'm going to condense these constants into a single constant just to make it easier. And also because we know that these constants are unlikely to be perfectly accurate because we just kind of, we made some assumptions that mean that the constants out here probably aren't totally accurate. So I'm going to write this as minus k v squared. So we've got some constant. This determines how strong the drag is. If k is bigger, that means that the force of drag is larger for any given value of velocity. So k is kind of a toggle to, or kind of a variable that determines how strong the air resistance is. And so how do we solve this? We can't just solve this algebraically in the normal way because acceleration will change over time as velocity changes. We're going to use a technique called separation of variables. So let me set this up a little bit further. So we know that acceleration is dv dt, the first derivative of velocity with respect to time. If I plug that into the equation, then I get something that looks like this. So it says the rate of change of velocity is proportional to negative velocity squared. So the way that velocity changes is proportional to velocity squared. Okay, we're going to use separation of variables to solve this. So what is separation of variables? So separation of variables, there's a couple of ways to think about what this technique is. First, we're going to treat derivatives like fractions of infinitesimals. So let me write that down. Treat derivatives like fractions. So that is, if I have this derivative dv dt, I'm going to conceptualize that as some small change in velocity over some small change in time. And if I conceptualize it that way, then I'm free to just kind of move these around as two individual parts. So what that could look like is I can do operations like this. M dv equals minus k v squared dt. Just multiplying both sides by dt. So that's the first step. If that seems fishy to you, it should, because that's kind of fake, but we can justify it. And I'm going to add a link for you with a more rigorous proof that this is valid, which I'm not going to go into here because it's kind of beyond the scope of what I'm trying to do. But just know that this is kind of the broad conceptual idea that you're treating derivatives as fractions, and it turns out that that works okay. The second thing is we're going to try to put each variable on either side of the equation. So put each variable alone on either side of the equation. So what that means is that right now on this side, I've got dv over here. So this is representative of some velocity variable. I also have v over here. So I'm going to move this to this side and keep dt on this side as representative of my time variable. So I'm going to do m dv over v squared equals minus k dt. So I've done what I wanted to. I just have time over here. That's the only variable I have. And I just have velocity over here. That's the only variable I have. Okay. I'm going to move the constants around to get them the way I want to. So I'm going to make it like this, k over m dt. Just put the constant terms on the right-hand side for my convenience. Okay, so now I have two things. I have a left side that only depends on velocity and a right side that only depends on time. And here's the last critical step for separation of variables. Integrate both sides simultaneously. So what does that look like? If I give you an expression like this, that's a perfectly well-defined thing. You can integrate that all day, no problem. And if I give you an expression like this, that is also a perfectly well-defined thing, and you can integrate that, no problem. And the claim is that I can set these things equal to each other because this is equal to this at every moment. So at every moment as our block is traveling, this is equal to this. So if I integrate over an entire motion, if I integrate this and I integrate this over the same set of times and same set of velocities, I get the same thing. So the equality of the things that go into the integral guarantees the equality of the fully integrated expressions. That's the argument here. If that also seems a little bit fishy to you, I agree. That can be addressed directly in the more rigorous proof that I add as well. But for now, it's kind of intuitive in a sense that kind of works. If this is always equal to this, then if you integrate over the same amount of time or the same change in velocity, you should get the same thing. So that's what we're doing. Let me move this up to conserve space a little bit. Okay. The last thing here is we have to be really careful because I said that we need to integrate over the same times and the same changes in velocity. So if time goes from 0 to some later time t, let's say, then we need to have a velocity at time 0, but we know that we started it with some initial velocity. So we'll integrate from the initial velocity to whatever the final velocity is. And I'll call that v as a function of time. So we're integrating from time 0 to a later time t, arbitrary time t, and we're integrating from the initial velocity to the velocity at some later time t. And ultimately, this is the thing we want to find. That's what we're looking for in this. So we're going to solve, we're going to integrate the left side, integrate the right side, set those results equal to each other, and solve for v of t. That's where we're going. So let's do this. So if I integrate the left side, I get minus 1 over v, evaluated from v naught to v of t. Okay, and if I integrate the right side, I get minus k over m t. The lower bound 0, so I don't have to worry about it in this case. So now I need to plug in the bounds for my left side here. If I do that, I get minus 1 over v at my arbitrary time plus 1 over v naught equals minus k over mt. I'm going to start moving stuff around and solving. So I'm going to multiply everything by a minus sign and move the 1 over v naught over. So I get 1 over v of t equals k over mt plus 1 over v naught. And I have a plus sign on that because I would have a minus for moving this over to the right side, but then multiplying by minus here gets me a plus there. Okay, so that's interesting. So 1 over the velocity is linear. So what does that mean? That means that the velocity is a function of time. If I invert everything, is 1 over this linear function. And that's my result. That's the velocity as a function of time. So does that kind of make sense? Well, let's take some limiting cases. So if time is 0, then this term goes away and I get 1 over v naught, which is just v naught. So when time is 0, velocity is v naught, that checks out. When time gets big, then the denominator gets big and the whole expression trends towards 0. So this is starting from v naught and going towards 0 in a 1 over t kind of fashion. That seems plausible. It doesn't seem wildly implausible. And let's take a look at it. So I'm going to pull up Desmos and we can look at this function. So give me 1 second here to pull up Desmos. All right. So I have plugged this function into Desmos. I've got it up here. and I've got these three constants, K, M, and V naught. So I've just arbitrarily set them all to 1 just to get a sense for how this works. And it looks like a 1/t that's been shifted over a little bit. You can see it starts at V naught, which is 1 here, and trends towards 0 over time. What happens if we play with these variables? What should happen? If the initial velocity increases, then this whole curve should shift up, because we would expect the velocity to start at the initial velocity. So if I change the initial velocity to 2, let's say, the whole curve shifts up. And you can see that happening. The drop off is still quick, but you can see the starting point shift up. But it's not just a pure shift of the curve. It's not just shifting the curve up. The decrease gets steeper, it looks like, as you increase the initial velocity, which makes sense because the force of drag goes quadratically with velocity. So if your initial velocity is higher, the force of drag on the block at the beginning is higher, and your velocity changes faster. Okay, so what happens if the mass is higher? If the mass is higher, we should still have the same y-intercept, but it should just be harder to slow down the block, because the inertia of the block is greater. It's just harder to change the velocity of the block. So if I turn up the mass, I should see this curve probably flatten out a little bit. So if I turn mass up to 2, looks like it's flatter. What if I turn it up, 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 like that? If I turn it way up, then it takes a long, long time to slow the block down, because there's just more and more inertia. What happens if I turn K up? So K represents the drag. So the bigger K is, the more drag there is. So I should see something inverse to what happened with the mass, which makes sense because of the way these constants are located in the equation. If I turn the drag up, the block should just slow down more quickly for the same amount of mass. So if I turn K up, then you can see that happening. And really it's about this ratio of K to M, right? So if I have K as 10 and M as 10, that's the same as if I had K as 1 and M as 1. I get the exact same curve because it's a ratio of K to M here, which is kind of interesting. So it says that kind of the drag constant there and the mass are doing the same thing, but opposite in a way, if that makes sense. There's one other thing I wanted to show you here. We solved for the velocity as a function of time. I'll leave it as an exercise to you to solve for the position as a function of time, which would just be integrating this velocity function from 0 to t. But I did that and I plugged it in here. So what does the position look like? Position looks like this. It ends up being a natural logarithm. And so this is maybe what you would expect. If we assume that the block starts at 0, the position increases over time, and it increases in a way where the slope decreases because the velocity is decreasing. That makes sense. But one interpretive point here that's not obvious and interesting is that log is unbounded. Log function's unbounded. So what this predicts is that the block will never actually stop. Its position will continue to increase as the velocity asymptotically approaches infinity, which is interesting, and a prediction of this model which is pretty non-intuitive, and which we would never actually see in the real world. So that would lead us probably to scrutinize the model, see what we left out, but is an interesting prediction of the model nonetheless. So I hope that helped as an introduction to separation of variables and to modeling air resistance, and I'll see y'all soon. Bye.